Next, let's talk about another algorithm to compute the importance of nodes in a graph, which is called helps and authorities, or HITs. And here HITs stands for hypertext-induced topic selection. And it's a measure of the importance of pages and documents similar to PageRank. And it's actually proposed at around the same time as PageRank, which is 1998. And let's say that we want to find good newspapers. And different from PageRank, which only finds good newspapers themselves, HITs not only finds good newspapers, but also find experts. And these are the people who link in a coordinated way to good newspapers. And the idea of HITs is similar to PageRank, and they both use links as votes. And the page, of course, is more important if it has more links. And remember that in PageRank, we actually use only the in links as votes, but the difference is that the HITs, they actually use both in links and out links as votes, and they use them for different purposes. And in the hubs and authorities algorithm, interesting pages fall into two classes. The first class is authorities, which are pages containing useful information. For example, newspaper homepages, which contains a lot of newspapers, or course homepages, which contain a lot of information about the course, or homepages of car manufacturers. So these are the content providers, and we call them authorities. And the second class is helps, which are the pages that link to authorities. And you can think of this as, for example, it can be a list of newspapers or course bulletin or the list of US car manufacturers. For example, let's say that in this graph, we have two large green circles representing two large authority sites. And we have the other blue small circles as hub sites. And we can see that the hub sites actually link to the authority sites. And these can be, for example, newspaper homepages, and these can be a list of newspapers. So corresponding to hubs and authorities, each page will actually have two scores. It will have a hub score, which measure the quality of the node of the page as an expert. And this hub score can be computed as the sum of authority scores that the page points to. For example, let's say that we have this graph of 9 nodes, and we have 1, 2, 3, 4, 5 authority nodes, and we have 4 hub nodes. And the hub score of this first node would just be the sum of the authority scores of node 5, node 7, and node 8. So basically, the hub score, H1, is equal to A5 plus A7 plus A8. And similarly, we have the authority score for each page, and these measure the quality of nodes as a content. And the authority score can be computed as the sum of hub scores that point to this page. For example, let's say that we want to compute the authority score of page 9, Wall Street Journal, and we can compute it as the sum of the hub scores of node 3 and node 4, because only these two nodes are linked to node 9. So basically, the authority score of node 9, A9, is equal to H3 plus H4. And note that this is actually a idealized example, and in reality, the graph would actually is most probably not 5 half-time. So in that case, each age will have both the hub score and the authority score. And once we define these hub scores and authority scores, we can use the principle of repeated improvement to iterate the updating of hub scores and authority scores until convergence. And then we can get the final hub scores and authority scores for each node. Let's look at an example. Let's say that we have a lot of nodes, and we have the nodes on the right here as the authority nodes, and we have the nodes on the left as help nodes. And we initialize the help score of each node here as 1. So we can start this process by computing the authority scores of these authority nodes here. For example, the authority scores of the New York Times would be the sum of the help score of the 4 nodes here, which is 4. And similarly, for this first node, the authority score of this node would be 1 plus 1, which is 2. And then we can go on to update the hub score of the hub nodes. For example, we can update the hub score of this node as the sum of authority scores of the nodes that this node points to. And specifically, since this node points to these 4 authorities, its corresponding hub score will be 2 plus 2 here, plus 4 plus 3, which equals to 11. We can see that these hubs actually collect authority scores. And then we can go back to update the authority scores of these authority nodes. And for example, the new authority scores for this first node would be 8 plus 11, which is 19. We can see that these authorities again will collect the hub scores. And of course, if we keep going, then we can see that all these scores will become arbitrarily large. So in reality, we usually will normalize the scores after each iteration. You may have noticed that we actually have a mutually recursive definition here. So basically, a hub score will link to many good authorities, and a good authority is linked from many good hubs. And this model actually uses 2 scores for each, and we have the hub score and authority score. And the hub score and authority scores as a whole can be represented as vectors H and A. And this algorithm HIT is actually very similar to the PageRank algorithm. We will first initialize the authority score for each node as 1 over the square root of n, and we will initialize the hub score of each node as 1 over the square root of n also. And then we can keep iterating these 3 steps until convergence. And let's take a look at what these 3 steps are. The first of the 3 steps would be the updating the authority score. We update the authority scores of each node as the sum of the hub scores of the inlink. So basically, we will collect all the hub scores for this particular node I. And then we will update the hub score for each node, and we update it using the sum of the authority scores that this node I points to. For example, to update the hub score of this node I, will just collect all the authority scores of these nodes, and we sum them up, and this is going to be the new hub score for node I. And then we'll normalize them. Basically, we'll normalize these hub scores and authority scores such that the sum of the square of all the authority scores equals to 1, and the sum of the squares of all the hub scores in the graph equals to 1. And we're going to update and keep iterating between these 3 steps until convergence. Now, we can see that this HIT algorithm is actually going to converge to single stable point, just like the PageRank algorithm. And to see this, let's first have a matrix or vector formulation for this algorithm. Let's denote as A the collection of all the authority scores for for all the nodes in the graph. Let's say that we have n nodes, and let's denote as H this vector to be the collection of all the help scores in the graph. And the adjacency matrix ij would be 1 if there is a link between node I and node j and 0 others. Then we can see that the equation of updating the help score can be rewritten as the sum of aij times aj, which is actually equivalent to h equals to a, this is capital A, times the small a. And similarly, the equation of updating the authority score can be rewritten in a matrix form as the equation here. Basically, A is equal to capital A transpose times H. And then we can write down the hit algorithm in the vector notation or matrix notation. We'll first initialize all the entries of A and H to be 1 over the square root of n. And then we'll repeat these 3 steps until convergence. We'll update H as the capital A times A, and we'll update the vector A, which is the authority scores, as the A transpose times H. And then we'll normalize the vector A and the vector H. Here, interestingly, we can see that this new A can be actually represented as A transpose times A times small a. Why? This is because this capital A times A is actually the new H. And when it's multiplied by the capital A transpose, we're gonna get the new A. And similarly, we can see that this new H can be computed as the A times A transpose times H. And this is already very similar to the power iteration, right? And from this, we can see that if the head converges to vectors H star and A star, then this H star is actually going to be the principal eigenvector of the matrix A times A transpose. And similarly, the final authority score vector A star will be the principal eigenvector of the matrix A transpose A. And next, let's take a look at a simple example where we have a graph of 3 nodes, Yahoo, Amazon, and Microsoft. And this is the corresponding adjacency matrix. And let's run the hit algorithm to see what it converges to. We can see that when they converge, the final hop scores of Yahoo is actually the highest. And in terms of the authority scores, both Yahoo score and the Microsoft score are the highest. This makes sense because Yahoo actually have a lot of links to a lot of newspapers and a lot of content information, right? And comparing the PageRank algorithm and the hit algorithm, we can see that these two are actually 2 solutions to the same problem. And the problem is, what is the value of a in-link from node U to node I? And in the PageRank model, the value of the link depends on the links into U because it propagates the scores received by U. But in the hits model, it actually depends on the value of the other links, both into U and out of U. This is because U has 2 scores calculated using the in and out links, and these are the hubs and authority scores, right? And interestingly, the destinies of PageRank and the hit algorithm are actually very different. And one became the foundation of the Google solution, and the other did not.